Okay, so yesterday we considered several different cases. There was case one, which was questions one and two, but then three and four there was case two, three, and four in questions three and four. In case two, they said, "Hey, suppose that Lenny and George started with 10 rabbits rather, and that each month they had each pair had two babies per month. So if we did that, we would start here with the 10, and then after a month went by, we would go to 20. And then after another month, because each one of those, there's 20 pairs there, so each one of those are going to have two babies. So we're gonna double the number of rabbits again. We're going to go to 40, and then we're going to go to 80, and then we go to 160, and the last one I fit up here is 32. So this is the pattern that we're seeing, and we can connect the dots if we want to do that. But if I'm thinking about whole months, I don't know that it makes sense to talk about rabbits in between, but it certainly helps visualize this curve better. This is an exponential curve, and it's not a parabola, but sure kind of looks like it to some of us right now. But today we're moving on, and instead of talking about rabbits, we're going to talk about rebound ratios. So there is a thing in sports that most balls that people use for particular sports have either in the rules or in the manufacturing, they're specified what the rebound ratio should be, or what the ball's bounciness should be. So many games depend on how a ball bounces. For example, if different basketballs rebounded differently, one basketball would bounce differently off a backboard than another. And this could cause basketball players to miss their shots. Right? Just imagine if you're training with one particular basketball, you go somewhere else and it's a whole different thing. So for this reason, manufacturers have to make balls' bounciness conform to specific standards. In this lesson, you will investigate the relationship between the height from which you drop a ball and the height to which it rebounds. Listed below are the bounciness standards for different kinds of balls. So a tennis ball must rebound approximately 111 centimeters when dropped from 200 centimeters. A soccer ball must rebound approximately 120 centimeters when dropped from 200 centimeters onto a steel plate. So that's an interesting distinction there. You don't even play soccer uh, on a steel field, but it has to rebound or recover 120 centimeters. So you drop it at 200 and it has to come back up to 120. A basketball must rebound approximately back up to 53.5 inches when dropped from 72 inches onto a wooden floor. That makes sense. We play basketball on wooden floor. Squash balls, those the blue ones, must rebound approximately 29.5 inches when dropped from 100 inches onto a steel plate at, and then they even specify the temperature, 70 degrees. So the bouncing ball, how can you determine if a ball meets expected standards? Your team, or your task with your team, calculate the rebound ratio for a ball. Your teacher will provide you with a ball and a measuring device. You'll be using the same ball again later. In fact, I think in tomorrow's lesson we're going to refer to the same one. Um, so make sure you can identify which ball you have. Well, so the difference is this here is we're not actually going to be able to collect this data, right? This is going to be a set of data that I give you, and the ball that you're going to be using, or that we're going to be using, is this specific one. It's these blue, I think they're called super balls or whatever, but they that is not. You can see this does not even come back up. It just barely came back up to where I dropped it from, way up here. So not great. So what I'm doing is I'm going to give you a set of data where I drop this from a specific height, and then I'm going to record carefully where it came back up to. So you're going to have the drop height and then the height it was recovered to, where we dropped it from and where it came back to. So a couple things to consider when we're setting this up to collect data. Um, Consider parts A through D below. Does the height from which the ball is dropped depend on the rebound height, or is it the other way around? I would say, does the height from which the ball is dropped depend on the rebound? No, I would say that the rebound height depends on where I drop it from. So because I'm saying that, and because that makes sense, we're going to say that on our x-axis, it's going to be the initial height, so where we drop it from. And then the rebound height will be our y-axis. That's going to be the dependent variable, right? So I would say we're going to say that the rebound height depends on the height that we drop it from. So with your team, decide which is independent variable. I just decided for us. Read the math notes box in this lesson. Should a graph of rebound heights versus starting heights be continuous or discrete? Okay, let's pause. Let's pause and read the math notes for this lesson. So the title of the math notes is Continuous and Discrete Graphs. When the plots on a graph are connected and it makes sense to connect them, then the graph is said to be continuous. Okay, so if we're connecting the dots and it makes sense in that situation, it's called continuous. If the graph is not continuous and it's just a sequence of separate points, the graph is called a discrete graph. For example, the graph below on the left represents the cost of buying X shirts, and it is discrete because you can only buy whole numbers of shirts, right? So if I was going to buy one shirt, you can see it's $15, two shirts is 30, three shirts is 45, etc. So I have I know no shirts cost me $0, and after that it's all increasing by 15 each time. The graph on the farthest right represents the cost of buying X gallons of gasoline, and it is continuous because you can buy any non-negative amount of gasoline. So we can buy gasoline that's like, we can buy 1.332 gallons, for example, and that would make sense on that graph. So continuous and discrete. So we are continuing then, and the two questions that you need to respond to today are question 20 and question 21. For 20, I definitely want to see well, I'm going to give you the table of the initial drop height and then how high it bounced up to the rebound height. But you need to give me a graph of that situation. Make sure you label the x-axis and the y-axis using Desmos. And then decide, should this be continuous or discrete. I think this I think it could be, I think I could drop it from any height, right? I could drop it from 62.31 inches, so then it would come back to something. So I think along the x-axis, I certainly can drop it from any height. So maybe this situation would be continuous, because if x is the height that I drop it from, there's nothing to prevent me from picking any initial drop height that I want. So in Desmos, there is the ability to turn on connecting dots. So once you have all your data in there, if you want to connect those, you can. Graph your results from problem 5-19 on a full sheet of graph paper. Draw a line of best fit for your data. Should this line go through the origin, why or why not? Justify your answer in terms of what the origin would represent in the context of this problem. So think about it. What is the x-axis, initial drop height? What is the y-axis, the rebound height, or the height that it recovered after one bounce? So should it go through the origin, why or why not? Write the equation of the line that models your data. If you want, if you look at it and it appears to be linear, you can use regression tools in Desmos to come up with the equation of the line that models your data. And then finally, what is the rebound ratio for your team's ball? So rebound ratio, right? What is it? Rebound ratio is the ratio, right? The ratio is just a division problem of the ball's rebound height divided by the initial height, right? Where did it rebound to divided by where did it start from? And if you think about that, I think that's the slope of this graph, right? Because the y-axis is where did it rebound back up to, and the x-axis is where did I drop it from. So I think that's what this is in context. The rebound ratio is the change in y and change in x, And in this case, y is the rebound height and x is the initial drop height. And I'm going to be honest, I gave you a lot there. I said a lot. So to be honest, I think I've answered most of these questions. So I just want you to do a quick, you know, one page in Google Docs, write up just a couple sentences. Make sure you include the graph in Desmos. Make sure you specifically call out the equation for your line of best fit. Make sure your x and y axes are clearly labeled. X, I'll say it again, x should be the initial drop height and y should be the rebound height. And then it says, how is the rebound ratio reflected in the graph of your line of best fit? Where is it reflected in the equation of your line of best fit? And how is it reflected in your table? And we will finish there. And then you're going to be going on to do the review preview for this evening. This is Mr. Roberts. I hope you have a good day, and I'll see you in class. Oh, and online. And remember, tomorrow, point recovery quiz. I'll see you later.